In this work, we study the aerial physical interaction problem of a flying end effector that consists of a fully actuated hexarotor with tilted propellers. We address this problem by developing an energy-aware impedance controller using the Port-Hamiltonian framework. We model the flying end effector in the Port-Hamiltonian framework as a single rigid body that characterizes the robot's kinetic and potential energy. The Port-Hamiltonian dynamic model describes the evolution of the robot's states, which are the configuration of the body fixed frame with respect to the inertial frame and the generalized body momentum. This dynamic model has two power ports, one which represents power supplied from the environment that we want the robot to interact with, and another one which represents the power supplied by the impedance controller. A standard impedance controller is interpreted in this framework as a virtual physical system with its own Port-Hamiltonian dynamics. The system consists of a first component that emulates a virtual spring attached between the robot's end effector's frame and the desired virtual frame. A second component that emulates a virtual damper connected between the robot's body frame and the inertial frame, and the third component that compensates for gravity. In order to regulate the interaction wrench applied by the robot to the environment, we designed the stiffness of the virtual spring to be variable, and we modulated using a wrench observer that estimates the interaction wrench with the environment. However, using this variable impedance controller, the controller's dynamics is no longer passive, which means that we cannot guarantee contact stability with the unknown environment. Thus, this controller is not safe for generic interaction. Our main contribution is in this work for guaranteeing contact stability and safe interaction with unknown environments is to extend the variable impedance controller using the concepts of energy tanks and energy routing. The intuitive idea of an energy tank is that it stores the energy dissipated by the control system and uses it to implement control actions that could violate the passivity of the closed-loop system, which in our case is the regulation of the interaction wrench. In order to avoid an unbounded increase of the energy in the tank, it is equipped with an overflow valve and an overflow sink to make sure a maximum energy level in the tank is enforced at all times. So, our energy-aware impedance control methodology allows the regulation of the interaction wrench while guaranteeing the contact stability with any passive environment. It is also geometrically consistent with the structure of SE3, the special Euclidean group. It also has the benefit of being modular, which allows upgrading the stiffness adaptive law or the wrench observer for performance enhancement. Furthermore, by exploiting bond graphs, we can conduct the closed-loop system specificity analysis just by inspection, avoiding lengthy analytical calculations. On top of that, energy tanks allow the energy flow within the system to be observed and used for embedding high-level control objectives. In our work, we proposed a method for dealing with potential contact loss when regulating the interaction wrench, which is based on monitoring the energy that is drawn from the virtual tank. Subsequently, the algorithm responds by altering the behavior of the energy tank, such that safe interaction is guaranteed. The intuition behind this safety extension is to freeze a large part of the energy in the tank as soon as a safety violation is triggered by a surge in the power entering the tank. In this way, we introduce an implicit hysteresis in the energy tank that provides contact loss stabilization. We call this new extension to energy tanks the energy freezing and melting algorithm. We validated our energy-aware impedance controller through a series of simulations and experiments in different scenarios and operation conditions. In the experiment shown here, the robot is commanded to exert a desired force normal to a fixed vertical surface with a force torque sensor attached to it. From the figures, it can be seen that the reference force is properly tracked by the controller through modulating the stiffness of the spring, as long as the energy level in the tank is higher than its lower limit. As soon as the energy tank is depleted, the valve gain alpha is closed, and consequently, the wrench regulation is aborted in a stable and smooth manner. In another experiment, we tested what happens when a standard variable impedance controller is used with an unknown environment. From the figures, It can be seen that the interaction force applied to this vertical surface is indeed being regulated. However, if for any reason there is a loss of contact between the robot and the surface, the controller increases the stiffness without limits until the robot crashes. On the other hand, if we repeat the same experiment with our proposed energy-aware controller and energy tank safety extension, the robot is able to detect energy spikes inside the controller due to the contact loss with the environment. Then the controller proactively turns off the stiffness modulation, which results in the abortion of the wrench regulation, and thus a safe interaction is guaranteed. So, we hope that we got you interested in reading our paper and attending our presentation at ICRA. Thanks a lot for watching, and see you in London.